Saxon's Trig, Lesson 40, the argument in mathematics, the laws of logarithms, and then properties of inverse functions starts on page 286. So part A is about this term argument in mathematics. And so it highlights the word argument, and it says in English, basically an argument is when you're having some sort of heated discussion back and forth between people. But in math, an argument has a different meaning, and it has technically three. So it's coming from the Latin word arguere, which means to make clear, which obviously so far this does not feel like we're making things clear, or to prove by showing the reasons. So if I'm proving something, that feels to me like a proof, but it doesn't have to do with proof. So they say, for this usage, we say that an argument is a connection of statements or reasons, that sounds like a proof, intended to establish or refute a given proposition. So that first definition does have to do with proofs. The second mathematical use is polar form for complex numbers. Again, they tell you this and then they never refer to it again, even dealing with the polars. And then the third is the length of the radius vector is called a modulus. So the third mathematical use of the word argument then is to establish in a function. All right, so it's kind of like the answer part when you're using the function format. So my basic summarization here is that an argument, and they're only using it in the terms of a function, is the answer to the function. All right, now that we've said all of that, we're going to leave it, and it rarely comes back up, although it might say find the argument in the function, and you just need to remember, oh yeah, that means answer. Okay, now there are rules in part B for logarithms, and that's what we want to take a look at here. All right, now they're embedded in here, and they don't make them very clear that these are their rules. So their first one that they're giving you is this one. If we have log base b, and you have two things that are multiplying together, what that means is that you separate log base b of the m and log base b of the n, and multiplying things are, in this case, adding with the separated logs. Log base b of m over n is what you think. Log base b of m, sorry, that didn't finish the b, minus log base b of n. And then, now they stop and do some examples. I'll come back to those. I just want to give you all three of them. So the third one is log base b of m that has an exponent of n. So when you have an exponent, the n is multiplying in front of your log base b of m. Okay, so now that you know those three rules, backing up to page 287, example 1, it says solve log of a4 plus log of a6 equals log of a x plus 4. Okay, so I need to recognize that all of the statements have a log base a. That's important. I can't do the problem if one of these is a log base b. They all have to have the same base, so I always check it first. The 4, and then the log statements are adding, so what I'm really doing is multiplying. So we're going to do 4 times 6 equals, and because they all had the same base, I basically picture slashing them off. So all that I'm left with for this equal is the x plus 4, and then we're going to solve for that algebraically. So 4 times 6, x plus 4 minus the 4, so x equals 20. Example 2 on the next page says we have log base 4 x plus 6 minus log base 4 of x minus 1 equals log base 4 of 5. Again, first thing I check, 4, 4, and 4. Yep, so I'm basically ignoring all of those statements. X plus 6 The minus tells me divide with x minus 1, and it equals the 5. So now to solve, this moves over to the other side and multiplies. So we keep x plus 6 equals 5 times x and 5 times negative 1. And then I would move this x to join, minusing, so that equals 4x. That means add 5 to this side, so there's 11. And then divide, and you would get 11/4. Where's the answer, example 2? Oh, there it is, 11/4. Okay, example 3 gives 3 log b of x equals log b of 8. Okay, do we have the same bases? Yep, log b, so I'm going to ignore those. But the 3 is multiplying in front of the log, so that means it's really the exponent over here. So it's x cubed equals the 8. What 3 times gives me 8? 2. 2 times 2 is 4, times 2 is 8, so x cubed, or you can do it on your calculator and cubed root on both sides to undo the 3 cubed root, and that's going to spit out 2. So however you think your way through it, you get 2. Oh, I should stop and clarify, just as a quick check, I always make sure log statements should not have negatives sitting beside them. They just don't work. So I should mentally throw back in my answers everywhere and just make sure that nothing should spit out a negative in this part only. So like 11/4 plus 6, that's certainly not going to be a negative. 11/4 minus 1, well, that's minusing 4 over 4. Nope, it's still in the positives. 2 goes in, it's a 2. 20 plus 4, that's not a problem. So I do it so instinctively as a quick check mentally, but I forget sometimes to tell you, yes, you need to do that. You might possibly lose a solution because it would make a negative, and then you would just say no solution for that answer. All right, example 4 gives us log base 12 of x equals 2/3 log base 12 of 64. So log 12, yep, so mentally I know I can get rid of those. So this is x equals, this is multiplying, so it's really the exponent, so 64 to the 2/3 as its exponent. Now, I don't remember if we've talked about this before. I think we did in some of the very, very early review lessons, but when you have a base with a fractional exponent, the numerator part is still acting as its exponent. It's like saying 64 squared. The denominator number is acting as the root number. So it does not matter whether you do 64 squared first and then cubed root the answer. Mentally, you might do better to say what number cubed root of 64 and then take that answer and square it. Either way, it's the same thing. So do we know a number 3 times that gives us 64? I think that's 4. 4 times 4 is 16 times 4. Yes, 64. That's what I thought. So 4 then squared is 16. So that's just a quick, easy mental way. Use the large numbers, but doing the denominator root part first makes it small enough to then do the exponent part easily. All right, part C, properties of inverse functions. And I quickly see that I have a box definition, so I know that it's something of extreme importance. And it says the definition of inverse functions. Now, when we talked about inverse equations, we took our x and our y and we flipped them and we plugged the y in where the x was and the x in where the y was. It's sort of the same thing with functions, but not quite. So in the definition it says 2 functions f and g are defined to be inverse functions if when you plug g into f, and that's what it's saying here when it's giving you this g plugged into f, and if that equals an x, you should get the same thing if you plug f into g's equation. You should get the same answer equals x. So that's what they're showing. And f of g or f of x plugged into g for all x's in the domain of f, and then they clarified for all x's in the domain of g. So in other words, it has to work for every single answer is basically what that's saying. So now that you kind of understand what the inverse thing is, you're supposed to plug G into F and F into G and check their answers. They give you two examples. Show that F of X equals 1/3 X minus 3, and G of X was 3x plus 9. I'm running out of space here, but I'm hoping I can do this. All right, so I'm probably can do the first one only. I'm going to pick up G, and I'm going to plug it in to F. So I have 1/3 multiplying with 3x plus 9 minus the 3. 1/3 multiplies with 3 and gets x. 1/3 times 9 gets 3 minus 3. 3 minus 3, oh, look, it's x. Okay, I might be able to do it. And then I'm going to do the reverse. I'm going to pick up F's equation and plug it into G. So that's 3 multiplying with 1/3 x minus 3 plus the 9. 3 times 1/3, 1 is x. 3 times 3 is minus 9. Keep the plus sign. Oh, look, they cancel. I got x both times. So yes, those are inverse functions. I'm definitely going to do example 6 on another page. Okay, show that f of x is given as 1/x minus 3, and they're much more difficult when they're in fractions. It's just easier to make a mistake. And then g of x is 3x plus 9. Show that they are inverse functions by computing. Okay, so we're going to pick g of x up and put it into f of x. So 1/3x plus 9 minus the 3. All right, nothing I can do with the numerator, 1/, and then I just need to put my like terms together. So this is 3x plus 6. And that's about as far, I think, as, okay, let me triple check. Did I make 1/3 x? Oh my goodness gracious, this is not F. No, I'm flipping problems. Goodness. Oh, stars. I was like, this does not feel right. Scratch all of this. G of x is not written correctly. I flip back to example 5. G of x is 3x plus 1. I'll try this again. 3x plus 1 over x. I knew that didn't feel right. Okay, G of x going into f of x. 1/3x plus 1 over x, that's that plugged in, minus 3. Okay, yeah, I knew it should look complicated. 1/, and these cannot go together unless they have a common denominator of x, which adds an x to the top. 3x minus 3x goes away, keeping 1/x. 1 divided by another fraction means flip the bottom one when you move it up to multiply. So 1 times x is basically x. Okay, we got that side. Now put f into g. So that's 3 parenthesis, and fill this in, 1/x minus 3 plus the 1 all over, x. I got to plug this in again, 1/x minus 3. I told you they get more complicated in fraction. Distribute 3/x minus 3 plus 1. Now I'm going to go ahead and fix that, since this is a plus, to have a common denominator, which will be x minus 3, which means the top needs x minus 3. Multiplying by 1 doesn't change it. All over top of 1/x minus 3, not doing anything with it yet. So 3 minus 3 cancels off, just keeps me x over x minus 3. Then this flips when I bring it to the top, so x minus 3 over 1. These cancel, and that just leaves me x. I have proven that these are inverse functions.